Can you guys please tell me what we have seen in the last class lecture? Maybe in the makeup class, in
Pipelining, sir.
pipelining. Okay, okay. Very good. So today we are going to start from there as well, where we have finished. Let me share your Jamboard file first. Wait. Okay. So in the last class lecture, we have seen pipelining. So this was all about the pipelining that we have actually seen in the last class lecture. From the slide, it was this pipelining energy. We try to understand the theoretical analysis of what is pipelining is using these examples. Like in single cycle, it took only 12 minutes to execute the task for three shirts in laundry. We had two resources, wash and iron. In pipelining, it took only 8 minutes, better than single cycle. If there is more than one task or one instruction is given, pipelining will always be better. Then we have seen the number of instructions and amount of time it takes in single cycle. Like in single cycle, add takes 600 picosecond, load word 800 in this way. We have seen for single cycle and we have seen how to find out the time cycle for single cycle and pipelining. If there is time given for every five stages that we have. Like in this example, time for register read and write. These are the five stages: IFID, EXML, WV. And type for five stages was like this: 100 picosecond for register read and write, and 200 picosecond for other stages. Okay. Then for single cycle, we found out this time. Load word takes 800, store word takes 700, maybe no, all of the or most of the R type instruction takes 600, but all BQ takes 500 picosecond. And we have found out that jump takes 200 picosecond like this in the class lecture. The jump takes 200 picosecond, other stages are idle. Okay. So for jump 200 picosecond it is working and 600 it is idle. So time cycle for single cycle is 800 picosecond. Addition of all the time of all the stages. IFID, EXML, WD. If we add all these things, we get this 800 picosecond. For single cycle, it is time cycle TC. And for pipelining, the time cycle is the maximum out of the all stages we have. And maximum time was actually 200, although three stages have had that, but this is the time you have to pick 200 picosecond, which is time cycle for pipelining. So for any example, we need to find out the time cycle before we can do anything here. Okay, and we have seen that if there is instruction like this, load word, load word, load word, and even after that a BQ comes, what will happen? We have seen these things in the pictures. Okay, I'm going to share pictures with you today as well. So just give me some time. Yes. And in the last class lecture, we have seen that our pipelining is always better. We have seen that pipelining works better than single cycle, but it has some problems as well. If we use pipelining, we are going to face some problems as well, and these problems are addressed as hazards. Okay, I'm going to show you, but this was the last problem we have seen in the last class. So if there is any problem, please do let me know. So today we are going to see pipelining problems or pipelining hazards. Okay, so hazards means problems in here in the pipelining, or we can say by the definition that situations that prevent starting the next instruction in the next cycle. What we do in pipelining, what we do in pipelining is we start the next instruction in the next cycle. If this is the first cycle, first instruction will start in the first cycle, second instruction will start their execution in the second cycle. So time cycle is 200 picoseconds. So this is first cycle, second cycle, third cycle, fourth, fifth, sixth, seventh, in this way. So if the first instruction starts in the first cycle, then second instruction will start in the second cycle within that time frame. Okay, third instruction will start in the immediate next cycle after the previous instruction, which is the second instruction. So if there is any situation that is preventing starting the next instruction in the next cycle, that is hazard. Up to now, we have seen we can easily start the next instruction in the next cycle. We can start the instruction fetch of the next instruction in the next cycle from the previous instruction. Like for this instruction, we have started instruction fetch in the third cycle from the previous cycle, which was the second cycle. So if there is any situation that is preventing doing us that, like starting the next instruction in the next cycle, then it is a hazard. And in pipelining, we have three hazards: structure hazard, then data hazard, then control hazard. Okay, these are the three hazards we are going to see in pipelining: structure hazard, data hazard, control hazard. Now we are going to understand one by one. The structure hazard, a required resource is busy. Now, the name of the hazard is actually the definition of the hazard. It is structure hazard. So, some problem, hazard is problem in here, some problem might be there in the structure of the pipeline. The way we have designed pipelining, there is that problem in that structure that a required resource might always be busy for the next instruction. Let me show you. Let me show you. In this example, we have started the instruction fetch IF for the first load word in the first cycle. In the first cycle, for the first 200 picosecond, that resource is always busy for second load word instruction, right? Please respond.
Yes, sir.
Pipelining is designed in a way that each resource can serve only one instruction at a time. So each resource cannot give more than cannot give service to more than one instruction at a time. So it will always be busy for other instructions. instruction fetch will be always be busy for other instruction. It is in the design. A required resource will be busy. Like for this second load word, sorry, for this third load word instruction, this instruction fetch was busy up to 400 picosecond, right? It wanted that instruction fetch resource. It was ready to work in the first cycle, but just cannot because this instruction fetch resource was serving a two instruction in two cycle. So this third instruction load word had to wait for 400 picoseconds because instruction fetch resource was busy up until 400 picoseconds for this third instruction. So in pipelining, in the design, except for the first instruction, every other instruction, this resource will always be busy up to some amount of time. Like for second load instruction, it is busy for 200 picosecond. For third load word instruction, it is busy for 400 picosecond. Maybe for the next instruction, it will be busy for 600 picosecond. And if we have for like 100 instructions in there, 100 instruction, or maybe 101 instruction, maybe we have to wait for 2000 picoseconds. Okay, so this is actually annoying, but it is in the design, we cannot improve it. Okay, so this hazard actually is in the diagram. This structure hazard, a required resource is this. And there is no way we can improve because it is the design, it is the procedure, and we have to follow. So we have to adjust this hazard. We cannot improve it. Everyone clear about structure hazard? Please respond. Everyone clear about the structure hazard?
Yes.
Okay, fine. Now we are going to understand what is data hazard is. And now for data hazard, we have some solutions as well. We are going to learn first what is data hazard is, then we are going to see that for this kind of hazard, we have some solutions as it is not in the design, but maybe due to the type of instruction with the registers. Okay, so we are going to first learn what is data hazard. For example, if the next instruction is waiting for previous instruction to complete its data read or write. Okay, so if one instruction is waiting for previous instruction to complete their data read or write, then there is data hazard related to data, so data hazard. So we are going to see some examples of that first. Okay, here is the example of data hazard. Only see these two instructions. Okay, I'm going to ask you some questions and you need to answer to understand what is data hazard is. Okay, so this is $S0. Can you please tell me, is this a destination or source register?
Destinations.
Destination. These two are source registers, right? In this sub instruction, this is destination, this is source, this is source. So what is destination in add instruction? That is source in sub instruction. Now, in our five phase, IF, ID, execution, memory, W back, we fetch the instruction from memory here, we read the source register, we execute the calculations. If any memory related work is there, we do, and then we write back the result to the destination register. Now, for add instruction, if for add instruction, whatever is in the S0 after the execution of the instruction, we want to read in this S0. As this is source in here in sub instruction, we want to read the S0 after the execution of add, right? For example, T0 has 2, T1 has 3. So 2 plus 3 is equal to 5 will be stored in S0, and we want to read that 5 in here. So we want to read this S0 after this add instruction, write back the result in this destination register, right? Please respond.
Yes, sir.
To do that, we cannot read this S0 before add completes this write back, right?
Yes, sir.
I'm going to show you this in the picture. So if there is anything like that, that the first instructions destination register is similar to second instructions or next instruction source register, then we have a data hazard. And what is that? For add, we can easily actually complete the execution. For add instruction, we can complete the execution. There is no pressure on us. Instruction fetch in the first cycle, then ID, then execution, then there is no memory related work, so we put it as an idle state. Then in the next 200 picosecond, we work for the write back, and write back is 100 picosecond. So 100 it is working, 100 it is idle. Okay, so we do the work of add perfectly. Problem arises when we want to execute this sub instruction in this pipelining. Normally, what would we have done? We should have started instruction fetch at 200 to 400, then ID at 400 to 600, right? But in here, as there is data hazard, this S0 is destination, this S0 is source. Whatever we want to read in here must be this value. And we have this value after this add instruction, write back the added value onto the destination register, and it does this work after 1000 picosecond. So before 1000 picosecond, we cannot start the ID instruction decode of sub instruction. Is it clear? Please respond.
Yes, sir.
Okay, so if I go to the next slide, you will be able to see. We have started the instruction fetching here from 200 to 400. Then there is that idle period. We cannot do anything in this time from 400 to 1000, because this is this should be done in order, like first ID, first IF, then ID, then EX, then memory, then WB. But as we have to complete ID after IF, and we cannot, ID is instruction decode or register read. So we cannot read this register if this add instruction doesn't complete its data write. That is why it is data hazard. So after add instruction completes its data write in write back phase, after that, only after that, we can start instruction decode for sub and then rest in the order. Is it clear to all of you? Please respond.
Yes, sir.
Okay, okay. So it is clear to all of you. Okay, this is clear to all of you. I'm going back to the slide. So this is data header. Please do not follow the slides timing diagram. It may confuse you. It's making a better use of the timing diagrams, but we just want to do it like this. We are going to start after 1000 picoseconds, not like these things in the slides. Okay, we are going to follow the pictures in here. Okay, so next thing is forwarding. Okay, before I go to the next thing, I'm going to give you some instruction in the chat box, and you are going to draw or sketch the diagram and let me know what is the completion time. Okay, using time cycle for pipelining as 200 picoseconds. Okay, so I'm going to stop the screen share. I'm going to give you some homework, some class work actually. I have given you three instructions in the chat box and you have to sketch the pipelining diagram. Okay. And tell me what is the total time required to solve this. Take some time and let me know the total time. Do it on your paper and let me know. Hello everyone. I guess it will be better if we solve this together. Okay, you guys are going to help me find the solution of these three instructions. I'm going to use a Jamboard to find out the solution. Okay, and you are going to help me to find the solution. So we have the same Jamboard in here. Remember, and these are the three instructions we need to find out the solution of. Okay, so I have just written this in here. I'm going to scale the timing diagram in here, and you guys are going to let me know what will be the uh, timing diagram in here for the pipelining. We assume same value, so we assume there will be only 200 picosecond of the time cycle. So it is 200. We are drawing the time cycle here. It is 400, 600, 800, 1000, 1200, 1400, 300. Then assume this is 18. This is 1000. Okay. So you guys please tell me for the first load word instruction where it should start. Okay. For the first load word. Instruction fetch should start in here, right? Please respond. Somebody
Yes,
has to
sir.
give me continuous response so that I can understand. Okay, so this is instruction fetch. Okay. Then in the next cycle we are going to do instruction decode. Remember, uh, we don't have to worry about the first instruction. It will be all okay always. Then in the next 200 picosecond it is execution. Next 200 picosecond as load word has this memory, so we are going to use it. It is really difficult for me to write in here in the Jamboard with the mouse. So it is WP for 100 and 100 idle. First load word is done. Second load word will start from here, right? Second load word. This will be instruction fetch, phase number 1, and this will be instruction decode. Actually, we have to write, I guess. If I write 1, we are going to write 1 in the answer script. So I am not going to take that chance. So this is ID. Then EX, as all are free, there will be no problem. Okay. Before drawing this, we have to see one more thing in here. Is there any data hazard between these two instructions? Similar source destination?
Yes, sir.
Where? Where is the
So
data hazard?
T0.
It is, I guess, the base address of the array, and using the 0 number index, it is using the 1 number index. So I guess these are not same.
I'm sorry, sir.
Okay, so no problem. You can make the mistake. It is normal. So there is no data hazard in between these two. But remember, data hazard, where it may happen. In the first instruction, if that is destination. In the next instruction, if that is source register. Like this. It is destination register in the load word. It is source in the add. So there is that data hazard, right? In between these two registers. Please respond.
Ji, sir.
For data hazard related examples, okay, for data hazard related examples, we have to identify where is that data hazard is. If we cannot identify, then it is really difficult for us to sketch the diagram. Here is the data hazard in between these two, destination and source. First instruction destination, second instruction source. If they are same, then there is data hazard. So for the first two instructions, there is no problem. We are going to do the sketching like this: execution, then memory. After that, in the next 200 picosecond, we are going to sketch the WB 100 working, 100 idle, because 100 was given for that. Okay, remember in the time. Now the problem arises when we are going to sketch for the add instruction. Last add. We can fetch it here. There is no problem in fetching in this time cycle. Remember, in this time cycle, we can fetch if, can fetch this. There is no problem. Now problem arises when we are going to use ID, because ID is instruction decoder register read. Can we use ID in here? Please let me know. As there is hazard
No, sir.
where we can start the ID of add, after
From
which
1200, sir.
1200. Very good. So after 1200, we can only start the ID. Up to now, this will be idle instances. When we can start our ID, then we can do our execution. Then we can actually do memory actually not there for add instruction. So it will be idle stage as well. For add, there is no memory related word. Then WB 100 working, 100 idle. So this is the time it finished. So total time. What is the total time? Can you please tell me? 200 picosecond. Sorry, 2000 picosecond, right? To execute this three instructions, please respond.
Yes, sir.
Okay, and number of cycles. Can you please tell me number of cycles? How many cycles are in there in 2000 picoseconds?
3, sir.
One, one, two, three, 4, 5, 6, 7, 8, 9, 10. If we divide this by time cycle 200 as Tc is equal to 200 time cycle. 200 picosecond. So if we divide this by 10, we are going to get there is 10 cycles needed to execute this three instruction. So now we understand how it is working. Data hazard, please respond. Is it clear?
Yes, sir.
Okay, now I'm going to go to the slides to show you the next instruction. So we have seen data hazard. Now we are going to see forwarding. Forwarding. Okay. Forwarding as known as bypassing, as well. We are going to forward the result when it is computed. We are not going to store it to be stored in the destination register. We are not going to be waiting uh, until it is stored in the destination register. We need a extra connection in the data path. Okay. Now I'm going to show you forwarding related picture. There is the picture. So we have seen data hazard. We have understand data hazard how it works. Now we are going to see forwarding. Same example, add and sub. But we are going to see forwarding. Now these cycles that are being idle in here, these are stalled cycles. Number of cycles stalled in here. Can you please count? In the normal data hazard design for add and sub, how many cycles were stalled? 1, 2, 3, right? Please respond.
Yes, sir.
In forwarding, we cannot remove all the stalled cycles, like 3 cycles, but we can reduce that number. Okay, we can reduce that number, forwarding or bypassing. Now, again, this is add normally done in the pipelining timeline. Now we are going to start sub. Yes, we can start the sub in here from 200 to 400 picosecond. We can start the sub in here, but where we are going to start the ID. Normally in data hazard, we start the ID after WB, but in this WB, if we look at the single cycle data path, it will be better for us. For add instruction, the value we write in this destination register, this value, right? Please respond.
Yes, sir.
So the value we want to write in the destination register is already prepared in this part, EX, as you can see, it is EX phase, right? The
Yes, sir.
value we want to store in the destination register already prepared in the EX phase, right?
Yes, sir.
Okay. So can we just forward this value, this direct value to next instruction source register, like uh, this calculated value to ID of the next instruction. If we do forward that value, this is bypassing or forwarding. We are not going to wait up until it is going to be stored in the destination register. Instead, we are going to forward this value from the EX from where it is being calculated. The result is calculated in EX. We are going to forward it from there. So go to the next picture. As you can see, we are using ID after EX, not after WB in forwarding method. And this is the solution of data hazard problem. Due to data hazard problem, we had to wait for 3 cycles. So this was the cycle stall, pre-cycle it was stalled for. Now in here the cycle stall is only one, right? Please respond.
Yes, sir. Skipping 2 cycles.
Okay. Now we have to sketch a line from EX to ID, although it is not showing in the picture, but you have to do it like this from EX to ID. Actually, this arrow should be from EX to ID, not somewhere in here, but from EX to ID. Okay, we are going to draw a direct connection from EX to ID. Let me show you in the Jamboard how it should be done. Like if we had forwarded from EX to ID, there would be this type of connection, EX to ID. ID would have been here, ID would have been here exactly after the EX if we had followed forwarding. So we should have sketched this type of arrow, like this, EX to ID, if ID was in here. Okay, so this is it. We understand the forwarding as well. And remember, in load word instruction, the destination register's value actually prepares in the memory part. So we have to forward from memory for loaded instruction. Let me show you that in the single cycle data part as well. For loaded instruction, whatever we want to write in the destination register, that result is being coming from this read data memory section, right? Not from execution. So if next instruction source register is connected with load word destination, then we can forward from the memory part, not from EX. Because the value we want to write in destination, it is being prepared in the data memory or memory section. So for load word, if we have, for example, load word destination is similar to sub source, then we can read this ID after memory, not before that. Is it clear? Please respond. Is it clear or not?
Yes, sir.
And as we have seen, even after why this picture is not coming down. Okay. So even after this forwarding, there is still a cycle stall. Still a cycle stall. To remove this cycle stall, we have to use port scheduling. Because for data hazard, if we use forwarding, we cannot remove all the stalls. Still, we have some cycle stalls, like one. If we want to remove that cycle stall, we have to use port scheduling. I guess you guys cannot see the picture. Yeah, I have to edit format shape. I guess this is good. Okay, you can see the lines of codes in here. Please respond.
Yes, sir.
Okay, so in here, these are the data hazards. As you can see, T2, T2, as in this is T4, T4. This is data hazard as well. This is data hazard as well. This is destination. This is source. This is destination. This is source. So all this is data hazard, and we need to overcome this data hazard using port scheduling. Now, even if we use forwarding for this data hazard, there will be a cycle stall, right? We have to wait for one more cycle still after the forwarding, right? Please respond. We have seen even after forwarding there is a stall of cycle. We have to wait for EX, right?
Yes, sir.
So assuming that there will be one stall for one data hazard, how many cycles it is going to take, we have to count. Normally, how many cycles it will take? In our pipelining diagram, if this is one cycle, second cycle, third cycle, first load word or first instruction will take 5 cycles, right?
Yes, sir.
Let me show you in this example. First instruction is taking 5 cycles up to 1000. 5 cycles. 1 cycle, 2 cycle, 3 cycle, 4 cycle, 5 cycle. If there is no data hazard present, every other instruction will add one more cycle, one more extra cycle, one more extra cycle, right? So every other instruction will add one more cycles to it. First instruction will be 5 cycles. Every other instruction will add one more cycle because of the structure hazard we have in here. Okay. So if we want to count the number of cycles in here, first loader will in pipelining, first loader will take 5 cycles, right? Please respond.
Yes, sir.
And every other instruction after that will take one more extra cycle. So one more extra 6, one more extra 7, 8, 9, 10, 11 cycles should be needed if there is no data hazard, right?
Yes, sir.
And for data hazard, we have one cycle stall extra. There is two data hazards, one in here, one in here. So 11 was the cycle needed if there was no data hazard. And now we have two data hazards, so two more extra. So 11 plus 2 is equal to 13 cycles will be needed for this number of instructions in here, right?
Yes.
Okay. So now we have to remove this data hazard using the reordering of the code. So reorder code to avoid stall in the next instruction or avoid use of load. Now, for example, if I can convince you in here, let me show you. For example, this is forwarding. This is forwarding. Now, in between this add and sub, for example, in between this add and sub, if we had another instruction, for example, that is load word and not connected to this add and sub, we would have started that load word in 200 to 400, right? Please respond. Please respond. We would have started that middle load word instruction from 200 to 400 and
Yes, sir.
done the rest of the work in here. And for sub instruction, we would have started this IF from 400 to 600, right? Then,
Yes, sir.
so if there was a instruction in between this add and sub, there would have been no stall, right? Right? Please respond.
Yes, sir.
So in between these two instruction, if there is a hazard, and if we can manage to insert a instruction in between these two, which will not change the order of the code, then or the original code, then we can remove that single stall as well, right?
Yes, sir.
So they have moved this line from here to the line in between this load and add. So this load word and add has a load word line in between that. That line will remove the stall that we had for this load word and stall word. Remove that stall, right? Please respond.
Yes, sir. But
And
sequence
now
doesn't
doing
change.
that, no, I guess it will not affect. These are not same registers. Sequence, we have to change the sequence. We have to reorder the code in a way to avoid the stalls. Now, doing that, you can see there is a more than one line gap between this load word and this add where there was data hazard. So their stall would be gone as well, right?
Yes, sir.
So now, as previously with the stalls, it was 13 cycle. Now, as we have removed two stalls, so two cycles will be reduced. So it is only taking 11 cycles now. Please respond after the code scheduling.
Yes, sir.
Okay. So we have seen data hazard that actually prevents the instruction decode in the next instruction. We had to wait until write back. Then we have seen forwarding from where the result is computed. We can forward like for EX or for memory where the result is computed. We can forward. But by doing this, we still suffer. We still suffer as there is still a stall of the cycle. Avoid that stall, we have to reorder the code. That is code scheduling. So data hazard has uh, two solving techniques. One is forwarding or bypassing. Another one is code scheduling. And we understand all of this. Now, last part, control hazard. Control hazard. Okay. Last part, interesting part. Branch determines the flow of control. If there is any instruction like branch on equal, branch on not equal, then there will be control hazards. If there is any branch instruction, there will be control hazards. And what is that? Let me show you it in the picture. Okay, you can see this picture perfectly. We have a add instruction. We are executing it perfectly. There is no problem. Then we have a BEQ instruction. Remember, BEQ instruction only have IFID EX. It doesn't have any memory or write back related work, right? Please respond.
Yes, sir.
Okay, okay. So in the add, there is no memory. In the BEQ, there is no memory and no write back. Now, you guys please tell me, after the execution of BEQ, let me show you in the single cycle data path, will help you. After execution of BEQ, this PC holds the key to next instruction. It can be PC plus 4 or jump address. So it can be either of there will be a jump or there will be no jump, right? And from where we can get to know after this execution phase, after we perform the subtraction, we get the value of zero flag. It will affect this marks and it will select the value for PC, right? So in branch on equal instruction, after the execution, we only know which instruction to fetch, right? Let me show you another example in the slide as well. Okay, for example, this is that code. Branch on equal S3, S4, IF. Now, after executing this instruction, we don't know either we are going to IF this, either we are going to fetch add or we are going to fetch sub. What will be the next instruction we want to fetch? We only can decide that after execution phase of BEQ instruction, right? Not before that. Again,
Yes,
if
sir.
we don't execute this execution phase, if we don't execute this execution phase, we don't know the value of zero flag. That value decides whether there will be a jump or not. So if there is a jump, we will fetch this instruction. If there is no jump, we are going to fetch this instruction, right? Please respond.
Yes, sir.
So, so can we fetch the next instruction before this EX?
No, sir.
So, for example, next instruction could be an instruction. For example, it is OR. It is OR. We have to fetch it after EX. Even if the IF resource is free or available from 400 to 600, even from 600 to 800, we cannot fetch it there because we don't know which instruction to fetch, because the instruction is branch unequal, maybe branch not equal. They decide the next instruction, right? They decide which instruction will be fetched in the next instruction, right? So before completing the EX, we cannot fetch any instruction. We cannot start the IF here in between 400 to 600 or in between 600 to 800. We had to wait until it is 800 picosecond to fetch the next instruction, and that is control hazard we cannot solve. Is it clear?
Yes, sir.
Perfectly clear. Okay, fine. So I guess there is no more picture after that. This is the last picture I wanted to show you. So I guess you have understand what is control hazard is. What is control hazard is. This is the thing we cannot fetch before we get the ALU in here. So any more question in today's part that we have seen? Let me review these things a little bit for you. We have started with this slide, pipelining hazard, structure hazard, which this is in the design, we cannot improve it. Control hazard we have seen for branch on equal or branch on not equal. Control action depends on previous instruction like BAQ, BNE. We cannot improve that as well. But for data hazard, we can improve that data hazard with forwarding and post scheduling. So these are the all things I wanted to show you for pipelining hazard. Is there any question? Any question? No question.
স্যার
So I am
এটা
just going
ইনস্ট্রাকশনের
to
উপর
stop.
ডিপেন্ড করে স্যার কোন
Share
হ্যাজার্ড ইউজ
recording.
করবে।
Yes. It depends on the instruction and the register. What is the destination register? What is the source register? All those things as well. So I'm going to announce the uh, third city schedule and syllabus as well now. And you're going to announce these things in your Facebook group and maybe in your Messenger group as well. So I'm going to write it down in the chat box. In the next week, we have a make out Saturday class in the Monday, so we don't have more than two classes in the next week, or one on Sunday, one on Wednesday. So in the immediate next class on Sunday, I'm not going to take your city three. Maybe we are going to see some new topic in the next class, and maybe in the Wednesday we can take the city, right? So city three syllabus is single cycle and pipe lining. Okay, date is next Wednesday. Let me check the calendar. Next Wednesday is 15th of September. So 15, 9, 2021. I have given the CT3 syllabus and schedule, and you have a week time to prepare for that. So next Wednesday we are going to give our CT3 on single cycle and pipelining. And in the Sunday we are going to have a new topic we are going to see in the class. Maybe if you want me to review something as well, I'm going to do that as well. So this is for the preparation of the CT3 and the new topics in next Sunday. And Wednesday we have our CT3. So CT3 announced in here. I'm going to stop the recording now. Now I'm going to